Okay, that's going. All right. Today we are starting definite integrals now. We've had a lot of intuition for what integrals are. We've already calculated some antiderivatives. I told you somehow this is encompassing an integral. Somehow antiderivatives give us area. So first we'll be going over a definite integral, the exact definition of an integral. Hopefully it's pretty intuitive after everything we did last class. And then next we'll be going over the fundamental theorem of calculus, which basically tells us how we can use antiderivatives to calculate integrals, so that you don't have to do it by hand. And you remember we calculated a few by hand last week, right?
Yeah.
Okay. So maybe come and get basic picture once again. Intuitively, what is an integral? Give me basic intuition.
It's you're trying to find the area of a line underneath a line.
Yeah, pick some curve, pick 2 points, A and B. Intuitively, the integral gives us the area under this curve. That was atrocious. Right?
Yeah.
And how does it give us that area? What do?
We find the antiderivative.
No. Based off of brute force, when we've calculated the integral so far, how did we do this?
Find an infinite amount of rectangle there.
Yeah.
We came up with some rectangular approximation. We said we'll approximate the area with a bunch of rectangles. Something like that. And then we'll use more and more and more rectangles
To get a better approximation.
to get a better and better approximation. Now, it's not enough to just use more and more rectangles.
Yeah.
We had to use more and more rectangles in such a way that the width of each rectangle was going to
Infinity.
0.
Zero.
The width
Sorry.
approaches 0,
Yes.
right? So it's not enough just to use infinite rectangles. We need to use infinite rectangles that all have a height somewhere on this line, whose widths all go to 0. Right?
Yeah.
Now, when we talked about the width of a triangle, just to remind you of some basic notation that we're going to see over here, we called this distance, we called the first point here, A, we also called it x0. This point we called x1, etc. And then B was also xn, right?
Mm-hmm.
As we partition this thing up into n little intervals that we're going to use to calculate our rectangles with. And we called the distance between, on our kth rectangle, we call that distance delta k, or delta x sub k. So this distance right here was delta x sub 1. That's this distance. This distance is delta x sub n. For our kth rectangle, it's delta x sub k. With me?
Yeah.
And we said for a random point somewhere on that interval, we were going to use x sub k for some random point in between, c sub k, sorry. For some random point in here, we were going to use c sub k. And that was going to be the point that we calculate the height at.
Mm-hmm.
So c sub 1 is some point in the first interval, c sub 2 some point in the second interval, c sub k some point in the kth interval, and then c sub n is some point in the nth interval.
Yeah.
So the area then of the kth triangle was the height at that point, height times width, right?
Yeah.
And our requirement when we calculated an integral is all these delta x's have to approach 0. Now, all these points, we call that a partition.
Mm-hmm.
So the largest gap in a partition, the largest interval in a partition, we call the norm of the partition, and we represent that as the norm of P if that's partition P. So this represents the biggest delta x.
Yeah.
So we want the norm to approach 0. That's how we want to take infinitely many integrals, or infinitely many rectangles. You with me?
Mm-hmm.
Yeah.
So what's the difference between an integral and an antiderivative?
We'll see.
Okay.
An antiderivative is just undoing a derivative. An integral is calculating what I'm talking about here.
But
definite
don't they
integral.
kind of say the same thing?
Yeah, they're very much related, which is why we're going to use antiderivatives to calculate integrals.
Okay.
But the definite integral from a to b is giving me the area under this curve.
Yeah.
An antiderivative is undoing a derivative. There's no reason for you to just assume that that somehow gives you area, or that can be used to calculate area. It's like you're asking me, what's the difference between multiplication and calculating the area of a rectangle? You can use multiplication to calculate the area of a rectangle, and that's how you do it.
I see.
Okay. So we use antiderivatives to calculate integrals.
So in a sense, an antiderivatives is kind of like an operation?
Yes.
Okay. That makes sense.
It's undoing a derivative. It's finding the function whose derivative gives you back the function you initially had. Okay. So now we've got basic intuition once again for what this integral picture was. Now we're going to go over the exact definition of an integral, and hopefully we don't lose you, a definite integral. Now, I'm going to give it to you the book's way. I hate the book gives it this way, but it's exactly what's in the book, so I wanted to go over it that way first. And then I'll try and make it simpler again, and then we'll go from there. So let's go over the book's way of saying this. Let f of x be some function defined on the closed interval a, b. With me?
Mm-hmm.
Yeah.
We say that the real number j, this is going to be the area. When you calculate the area, you get a number, right? So we're going to say that j, the area that we calculate, is a real number, is the definite integral of f on ab. So j is the area of f on ab. And that j is the limit of the Riemann sums. Let's remind ourselves of the Riemann sums. So once we have this picture, a Riemann sum then is this. From k equals 1 to n of f of c sub k times delta x sub k. Here's the Riemann sum.
Yeah.
Okay. So j is the definite integral, and j is the limit of the Riemann sums. Oh, I wrote it right here. This, so the limit of this, provided that for every epsilon, there exists a delta, such that for every partition with n parts of the closed interval AB, with the norm less than delta, so the norm's getting smaller and smaller,
Okay.
the biggest gap's getting smaller and smaller, we have the absolute value, we have the distance between the limit of this sum and j less than epsilon. In other words, I should have done delta p less than, or norm of p less than delta. Let me write it a different way. Way that we're more used to seeing. I'm just trying to follow the book. And I need to rewrite this a little smaller. Of the closed interval AB with the absolute value, this is going to look kind of weird because I'm going to have a lot of vertical lines, but make sure you understand. Absolute value of the norm of p minus 0 less than delta.
Yeah.
So, if the norm is within delta of 0, then the Riemann sum is within epsilon of j, which is our actual area. So as the norm gets closer and closer to 0, the Riemann sum gets closer and closer to j. That's when we call j the value of the integral.
Gotcha.
Now, that definition is a big hunk of mess, and it's not using stuff that we've already developed previously. So let's go back and think about the exact definition of a limit. What does it mean to say that the limit as x approaches c of f of x equals L? What's the exact definition of that? It means for every epsilon there exists a delta such that if x is within delta of c, then f of x is within epsilon of L. Right?
Mm-hmm.
So, then saying that the definite integral from a to b of f of x dx is equal to j is logically equivalent to, and you'll see what this is all trying to say now in a much more concise way. The limit as the norm approaches 0 of this sum is equal to j.
Mm-hmm.
Notice that if I plug in the definition of a limit to this thing right here, if I use my definition of a limit to this thing, it tells me this. It says it's the norm gets within delta of 0. We have this sum gets within epsilon of j.
Yep.
That's what it means if we just rely on the definition of a limit. So this is how I think he should have given it, just like this. rather than with all these words, because we already know what a limit is if we go back and remember the definition of a limit.
That's what you gave us last week.
Yeah, so that's why this is such a wordy definition. It's because he's like redefining a limit at the same time,
Okay.
rather than using the fact that you already know a limit. So if you just remember that the limit, what the definition of a limit is already, this is just reusing the definition of a limit again. And so this is a much better way, much more precise way to write it.
Okay.
Now that's using the j so that you can see the j's in its definition. Here's how I would have really written it if I was writing the definition. I would say it like this. The integral from a to b of f of x with respect to x is logically equivalent to this limit. It's a limit as the norm approaches 0 of these Riemann sums.
Okay.
That's what it is. How do you calculate an integral? You calculate this thing. Which is what we did, right?
Yeah.
Now, this is very generic. We typically use a special case of this when we calculate our integrals by hand. This says, so we're calculating the limit as the norm goes to 0 of our delta x's. As our biggest delta x goes to 0, in other words, is what that's saying.
Okay.
So, as long as this definition holds, as long as the biggest gap in our partition is going to 0. So we can choose to evenly divide up our rectangles.
Okay.
And then if we choose to evenly divide up our rectangles, if we divide the segment up into even pieces, the length of each segment is always going to
Stay the same.
0. If we evenly divide it up. If I divide
Oh
my...
yeah, because each one's going to 0.
Right. Because if I take the distance from B to A and I divide it into n pieces, then this is the length of each of those intervals, B minus A over n, right?
The length.
The length of the base here.
Isn't that the width?
Sorry, same thing.
Okay. Okay. Yeah.
Yeah. So this is the width of each of those. So if we do the limit as n approaches infinity, then we see that the base approaches
0.
0. So the gap of our partition is going to 0.
Okay.
You see that?
Mm-hmm.
These are still just widths, and then these are just heights at the right-hand points. The definition tells us I can use any point in the interval. The right-hand point is a point in that interval. So here's the right-hand point. This says I can use I can divide it up into any rectangles I want, as long as their width is going to 0. I may divide it up into even rectangles, and notice that their width is still going to 0.
That's right.
So this is a special case of this definition. So we can use this to calculate integrals.
Can we use that for basically all integrals, or are there like special cases?
There's always special cases, but for the most part, yes. Every time I've calculated an integral by hand, I've used this equation, or something real similar to it.
Okay.
Sometimes switch it up a little to give students an idea of what it looks like when you use the left-hand points or the midpoints, whatever. Hardly changes though. Because all that changes is whether you put, if you start k equal to 0 to go to n minus 1, or putting a there, maybe instead you put a plus 1/2 if you want to use midpoints going from 0 to n minus 1. Doesn't matter. The point is, yeah, you can use that for almost every integral that you have to calculate by hand.
Okay.
Okay. So that is exactly what we mean by a definite integral. We mean this exact limit. And typically you can think about it this way if you want. It's a special case, but it will guide your intuition correctly. Now, important note, there's nothing special about the fact that we're using x's in here. I could have just as easily written that the integral of f of x with respect to x. I could have just as easily written the f of u with respect to u. I could have just as easily written f of z with respect to z. We call these dummy variables.
Okay.
Doesn't matter what you choose. We typically use x, but there's nothing holy about x. It's just
What if
simple.
it's a constant?
By plugging a constant into a function?
Yeah, what if it's f of c dx with respect to x?
Oh, the integral of c with respect to x?
Yeah.
We will calculate that exact integral.
Okay.
But no, there's nothing special about the variable x. Okay. Now, if f is continuous on a closed interval AB, or has at most finitely many discontinuities, then, jump discontinuities, then we can calculate an integral for that thing. So let's get intuition for what this means. Then the integral exists in, should be
It
calculable.
exists in that one area of the function, right?
Let me explain to you what exactly this is saying, and then we'll go over it.
Okay.
So this is saying, if I have a function, here's a, well, I'll mark those off afterwards. If I have some function, and my function, whatever it's doing, so it comes along like this, then it jumps down, like that, and then it comes back up here, and it goes on its merry way. And we're going to do this from the point A to the point B. Notice that on the interval A to B, this function is continuous, except at 2 points, it has a jump discontinuity. That's what we mean by, if f is continuous on AB, or has at most finitely many, 2 is a finite number, finitely many jump discontinuities, then the integral exists.
You're going to prove that?
So, no, unfortunately we can't prove this, so just give me intuition for the theorem.
Okay.
So let's get intuition for how we can calculate the area under this curve. Well, we can split this up into 3 sections. We can calculate the area from this point to here and get this area. Then we can calculate the area from this point to here and get this area. Then we can calculate the area from this point to here and get this area.
So you do like 3 different calculations? Right?
Possibly.
For this specific one, yes, right?
Or you just make sure that you include these specific points as points in your partition when you're calculating your integrals. If I were doing a rigorous proof, we'd manually insert those points into our partition. But
Okay.
now there is one point worth noting. Well, no, that's too much of a side detail. I think you get the intuition. As long as you got the intuition, we're pretty much about good. So unfortunately, proving that rigorously requires us to have been rigorous from the beginning. That's of course called real analysis, which we're not doing here. But as long as there's only finitely many discontinuities, we can calculate the area.
What does it look like if it has infinite discontinuities? How does that work?
Let's look. Next example. So, next example, look at this function from 0 to 1. So, here's 1, here's 1. Whatever, doesn't matter. And let's graph this function really quick, and then try to calculate the integral from 0 to 1 of this function.
Okay.
Now, what does this function say? F of x, it spits out a 1 if you input a rational number. It spits out 0 if you input an irrational number.
Okay.
So if I plug 0 into this function, what do I get?
1.
1. If I plug 1 into this function, what do I get?
1.
1. If I plug a half into this function, what do I get? 1. And for any fraction I plug into this function, I'm going to get 1, right? So I'm going to get a bunch of 1s up here. I can't draw all of them because there's infinitely many.
Why isn't it just a straight line?
Because I don't want confusion. Because what happens when I plug root 2 over 2 into here?
0.
I get 0.
Root 2 over 2 is 0?
It's irrational.
Root 2 over 2 is an irrational number.
Oh. and the
When I
output
plug
is
in an
0.
irrational number, it spits out 0. So root 2 over 2, what is that? Some number between 1/2 and 1.
Yeah.
So somewhere in here. So it's down here.
And can you have infinitely many of those?
Yes, there's infinitely many rationals, there is infinitely many irrationals. In fact, even though they're both infinite, there's more irrationals than there are rationals.
Okay.
So, there's also an infinite amount of irrationals all the way throughout here, which is why I'm not just drawing a solid line.
I see.
Because I don't want you to think that it's not all one function. It is one function. For every input, there's only one output. So it passes the vertical line test.
Okay.
We just can't plot these things. Because there's no way to do it. Because the only way to do it would be what you're saying, because we have to use, when we make a point, we can't draw a point and have it be a point, because a point has no size.
Yeah.
And if I'm going to plot a point, I have to use size. And so I can't draw both these functions without drawing two vertical lines, which is misleading, because that's not what it is.
Okay.
Okay, so that's what the function looks like.
Yeah.
Got some intuition for it?
Mm-hmm.
Now the question is, what's the integral? So we need to split this thing up into a Riemann sum. We need to break it up into a bunch of rectangles, right?
Yeah.
And we need to calculate the height times the width of each of those rectangles and see what we get. You with me?
Yeah.
So I'm going to do this two different ways. I'm going to use what we call the upper sums, the upper rectangles, and the lower rectangles. The upper rectangle, I'm going to use the highest point that the function reaches to calculate the height of my rectangle. And the lower sum, I'm going to use the lowest point that the function reaches on that interval to calculate the height of my rectangle.
Okay.
You with me?
Okay.
Good?
Yeah.
So for my upper sums, I'm going to use a sum from k equals 1 to n of, we'll call it f of x sub m, big M for the max point, the max height in that interval, times my width. I'll call it big M sub c. Big M sub c, the point that gives me the highest height in that interval. And for my lower limit, I'm going to calculate the integral as k approaches 1, or my sum as k approaches 1 from f at the smallest height on that interval. So I'll use little m sub c for minimum,
Okay.
or sub k, not sub c, sub k. It changes with k, sorry. Times delta x sub k. You with me on both those?
Yeah.
Wouldn't the upper just equal 1 then?
So the upper is just going to equal 1. The height is always 1, right?
Yeah.
So let me erase my picture here. I think you got the picture in your head, right?
Mm-hmm.
So doesn't matter how small of an interval you're talking about. Any interval on the real lines contains an infinite number of rationals and an infinite number of irrationals. Doesn't matter how small the interval is.
Yeah.
Okay? So it will always contain an irrational point. The height at every irrational point is
0.
Oh, is that what it was?
Yeah.
It will always contain a rational point, I meant. And the height at any rational point is?
1.
So this is equal to just the sum from k equals 1 to n of delta x sub k, right?
Yeah.
And this is just summing up all those little intervals. What do all those little intervals add up to?
1.
1. Because we're doing the sum from 0 to 1.
Okay, I see.
So that is equal to 1. Let's calculate this one. What's this equal to?
Well, since f of small m sub k is just 0, then it's just 0.
Now we take our limits. What's the limit of 1?
The limit of 1?
Yeah. What's the limit as the gap goes to 0 of 1?
1.
1. The limit of constant is constant.
That's right.
Doesn't matter.
Okay.
Take the limit as doorknob goes to sun. I don't care what limit you're taking. When you take a limit of 1, you get 1. Whatever that limit is doesn't change 1.
But what are you approaching, or does that not matter?
Doesn't matter.
Okay.
Doorknob approaches sun. 1 is still 1.
Okay.
N approaches infinity. Partition gap goes to 0. Doesn't matter. 1 is 1.
Yeah.
You with me?
Yeah.
Okay. Similarly, 0 is 0. So we have the limit. Well, let me write this way so I don't have to write this big sum again. So what did we just calculate? We just really calculated that the definite, no, I need to use the limit. Okay, we just really calculated that the limit as the gap goes to 0 of our sum from k equals 1 to n of f of c sub k times delta x sub k is equal to 0. And we also calculated it's equal to 1.
But how can it be two different?
It can't be. Going back to when we first talked about limits. If you calculate a limit one way and you get one value, and you calculate a limit another way and you get another value, that's a guarantee the limit doesn't exist.
That's right.
So the limit doesn't exist. So you cannot calculate this integral.
Doesn't the number, like when you're on the line and you calculate the upper, isn't that usually higher than the lower one is? Which still isn't the same thing.
They approach the same thing. The upper is always greater than or equal to the lower. In the limit, as you use more and more rectangles, they get closer and closer to each other, and their limit are the same value, if it's integrable. So it doesn't matter how you use the rectangles.
Okay.
It doesn't matter which point you use. The point that gives you the highest height, the point that gives you the lowest height, doesn't matter. C sub k. Any point in the integral.
Yeah, remember how he gave us the example and he ended up getting the same thing when we did the other way? If you remember. I don't know if you did.
Did we do it calculating it with an upper integral and a lower integral?
Yeah,
Or
and then
a right-hand point calculation, a left-hand point calculation? The limits come out the same. If it's integrable. Okay. So that's how we know this limit doesn't exist. We just got two different values. You can't have two different values. Perfect. Okay. Properties now of integrals that are worth knowing. Hopefully these are pretty intuitive to you. If you keep in mind what's an integral, it's an infinite sum. An integral, it's an infinite sum. That's what it is. Right?
okay.
So if you keep that intuition in mind, then hopefully we can calculate each one of these. This is supposed to be the integral from b to a. Okay. So first question. If I get that my integral from a to b of f of x with respect to x is equal to some number 10, that was base times height of the rectangle going from a to b. We have base times height of this, times this, times this, da, 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 all the way through and we got 10. Question now. What would be my integral be if I went from b to a? What happens if I calculated it backwards?
It's the same thing.
Is it going to be the same thing? What happens if I calculate it the other way?
It's still the same distance.
So look at this formula, right?
Yeah.
What happens if I swap around my a's and my b's?
You'll get negatives.
Oh, yeah, you get something with it.
You get negatives instead. You get the same thing, just negative.
Okay.
If b minus a gives me positive 3, then a minus b is going to give me negative 3. So when we flip it around, when we go from b to a instead of a to b, all that does is gives us a negative number. So the integral from b to a is equal to negative the integral from a to b. So if you don't like the order, we call these your bounds. If you don't like the order that your bounds are in, you can flip the order by just adding a negative sign. Does that make sense?
Mm-hmm.
Okay, next. What is the integral from a to a of f of x with respect to x? What is the area under a point?
0.
0. Now that's actually a definition. We define that to be the case, but hopefully the definition appeals to your intuition. Good?
Mm-hmm.
Okay. The integral of a constant times a function is equal to, what do you think?
The constant times.
The constant times the integral of the function. Remember, an integral is just an infinite sum.
Yeah.
If I have a constant times a term in an infinite sum, I can just factor the constant out of the sum.
Didn't we do that last week?
We did that with sigma notation.
That's right. So it
And
works
this,
the same
if
way.
we were to prove this, we would just use effect that's true for sigma notation. And then we use effect that's true for limits. We know in sigma notation we can pull constants out. We know when we're taking limits we can pull constants out. And so we pull it out twice, and there she is.
What's the difference between sigma notation and Riemann sums? Or
Sigma notation and what?
the Riemann sums?
Oh, the Riemann sums.
Riemann.
A Riemann sum is just a particular sum. It's a sum of rectangles.
Okay, but it uses sigma.
But it's using sigma notation. So sigma notation is just this part. But in your homework, you use sigma notation for a bunch of things.
Yeah.
They weren't always rectangles. Sigma notation for these rectangles is what we mean by a Riemann sum. Okay, next. The integral of a sum of two functions is equal to
Sum of the integrals.
the sum of the integrals. And once again, it has to do with the fact that the sum of two sigmas, or a sigma of a sum, is equal to the sum of the sigmas. And then we have our limit. The sum of the limit is the limit of a sum is the sum of the limits. So we're just using the fact that it's true for sigma notation and it's true for limits. It means it's true for integrals. Because integrals, just bringing those two together, it's just a limit of a sum, right?
Yeah.
So this gives us the integral from a to b of f of x with respect to x, plus or minus, doesn't matter if we were doing addition or subtraction, the integral from a to b of g of x with respect to x. So if you're adding two together, an integral of a sum is the sum of the integrals, an integral of a difference is the difference of the integrals.
Alright.
Okay.
And the integral of a product is the product of the integrals, right?
No.
No, not necessarily. Remember, that didn't work with our derivatives either.
Yeah.
The derivative of a sum is the sum of the derivatives. The derivative of a product, got to use a product rule.
Yeah.
That's right.
And when it comes to integrals, there's also an even harder product rule to use, and an even harder quotient rule to use. So no, it does not work with quotients, does not work with products, just like derivatives. Make sense?
Yeah.
Okay, next one. The integral from a to b of f of x with respect to x, plus the integral from b to c of f of x with respect to x is equal to
The integral of a to c.
the integral from a to c of f of x with respect to x. If you think about this as areas, that's pretty intuitive. Calculate the area from a to b, then calculate the area from b to c. What did you do? You calculate the area from a to c.
Yeah.
Okay. Next one. Well, this one's the least intuitive of them, I think, so we'll actually prove this one. But let's make it make sense. Let little m equal the minimum height the function reaches on the interval a to b.
Okay.
It's the absolute min on that interval a to b. Remember, the extreme value theorem tells us there has to be at least one. So I'm guaranteed little m exists if f is continuous on that interval.
Even if it's the same as everything else.
Even if it's a constant function. A constant function, every point's the absolute min and absolute max. Function has at least one absolute min and at least one absolute max on that interval. Extreme value theorem. It takes on extreme values on that interval. Remember that?
Yeah.
So we'll call the minimum little m, and we'll call the maximum big M. And let's draw a picture really quick to help us get intuition for what this is saying. So we'll just make it an obvious curve so that we know where big M and little m are. Something like that. Here's A. Here's B. Here's what we're going to say. Little m times b minus a. What does that give us? Little m is this height. Big M is this height, right?
Mm-hmm.
So little m times b minus a is the area of this rectangle. You see that?
Mm-hmm.
Yeah.
Big M times b minus a is the area of this rectangle. Right? Okay, so now I think this will make perfect sense. So let little m be the min on that interval, big M be the max on that interval. Then little m times b minus a, that small rectangle, is always less than or equal to the actual area. which is always less than or equal to the big rectangle.
Why is this useful?
We will use it in a proof over there.
Okay.
But that makes pretty good intuitive sense.
Isn't it basically just finding like the left hand and the right hand, just the absolute of that?
Just this is only one rectangle. This is a sum of infinitely many rectangles. This is doing it all with one rectangle.
Oh, I see. I see what it's doing.
So this is saying approximate the area using the minimum value and only one interval, i.e. the whole interval. And this is saying do it but using the highest point. Whereas this is calculating the actual area using infinitely many rectangles on the scene. Right?
Yeah.
So small rectangle, actual area, big rectangle. And those are always going to be sandwiched like that. Does that make intuitive sense? Do a proof of that one, but first let's make this last one make sense, and then we'll be good. If f of x is always greater than or equal to g of x on the interval, so let's draw a picture of this one. So here's my f of x. Here's my g of x. Here's my interval a, b. Notice that f of x is always greater than or at one point equal to g of x, right? Something like that. So if f of x is always greater than or equal to g of x on the entire interval a, b, we don't care what they do outside that interval, then the area under f of x is greater than or equal to the area under g of x.
Yeah.
Pretty straightforward, pretty intuitive. And once again, why is that going to be useful? It means that we can, if we have an integral that's hard for us to work with, maybe we can calculate something that we know is higher than it, that's easy to work with. And that can tell us something about the one that we're having a hard time working with.
Okay.
Okay, so those are our properties. And let's move on, we'll prove property 6, since I do a proof with it later. And that should be good. Okay, so proof, coming down to our proof number 6. So let f of x be integrable on the closed interval a to b. Integrable just means you can calculate an integral of it. The integral exists. And let little m be the minimum value of f, the absolute min of f on that interval, and big M be the max of f on that interval. And we know that those points exist by the extreme value theorem. So we're guaranteed those points exist. Okay, then what are we proving? Then prove that m times b minus a is less than or equal to the integral is less than or equal to big M times b minus a. That's what we're proving. Make sense? All right, so let's prove this. It's mostly just a bunch of algebra. I think you'll be able to follow it okay. So observe that m times b minus a, little m times b minus a is equal to little m times the sum of all the little intervals. If I add up all these little intervals, all my delta x's, if I add them all up, I get the whole distance from a to b,
Okay.
which is b minus a.
Yeah.
So b minus a is the exact same thing as this sum. No, we're up here. B minus a is the exact same thing as this sum. You with me? Okay. Now I know that I can move my constant inside my sum. Nothing wrong with that, right?
Yeah.
Now m is the smallest value the function achieves on the closed interval ab. So if I replace m with the height at a bunch of random points inside of the function, inside that interval, I could have only made my sum bigger. I couldn't have made it smaller. I'm guaranteed that f at some point, doesn't matter where, is always greater than or equal to little m. Because little m is the absolute min.
Yep.
So maybe I didn't make it bigger. Maybe I chose a point at the same height. But I could have also chosen a point higher. I definitely didn't choose a point lower. So I could have only made my sum bigger. Does that make sense? Good?
Yeah.
And then whatever my random point is, it could not have been higher than my max point. So this is less than or equal to that. You with me?
Yep.
Max point, I can factor out the big M out of my sum. And then when I recalculate that sum, I get M times B minus A.
Okay.
So we didn't finish the proof yet, but notice the pieces that we have together. We have little m times B minus A is less than or equal to our Riemann sum is less than or equal to big M times B minus A. Right?
Mm-hmm.
Now I just need to take the limit of those three things.
Okay.
If I know that, going way, way back, if I know that f of x is always less than or equal to g of x, then I know that the limit of f of x is always less than or equal to the limit of g of x, going back to our limit rules.
Yeah.
So that's what I'm going to be applying here. So I know that this is always less than or equal to this, is always less than or equal to this. Therefore, the limit of this is less than or equal to the limit of this is less than or equal to the limit of this.
But we're not trying to find the limit, are we?
We're trying to prove that the integral is sandwiched. The only way to get an integral is to take a limit.
That's right.
So I'm going to take the limit of those three things. So the limit as n approaches infinity of m times b minus a is less than or equal to the limit as n approaches infinity of this whole thing is less than or equal to the limit I jumped.
No?
No, I didn't jump. That line's confusing. Okay, second line. Here we go. The limit as n approaches infinity, sorry, that should be the limit as the norm approaches 0. I'm just used to writing n approaches infinity. The partition gap approaches 0. So the limit as the partition gap approaches 0 of little m times b minus a is less than or equal to the limit as the partition gap approaches 0 of the Riemann sum is less than or equal to the limit as the partition gap approaches 0 of big M times b minus a. Right?
Mm-hmm.
But what is the limit of this?
Just it. Whatever.
Just m times b minus a, that's just a constant. What is this limit? That's the integral by definition. And what is this limit? That's just big M times b minus a. Those are just constants. So we're done.
Okay. Yeah.
Good?
Mm-hmm.
It's not that complex, it's just a lot of notation, so it might be easy to get lost in the notation. But I think the idea is straightforward. Good? Okay, so now let's do some examples, getting us a little bit comfortable using these properties of integrals. So let's say, switching gears, doing an example problem now, done with that for now. So let's say I have some function f. I have no clue about this function f. I just know that the integral from -1 to 1 of f is equal to 5.
Okay.
I know that the integral from 1 to 4 of f is equal to -2. That's a -2.
Are these all the same f of x functions?
Those are both the same.
Okay.
And I know that the integral of h of x is equal to 7 from -1 to 1. Okay?
Okay.
That's just what I know. Gonna try and calculate some things now. So what's the integral from 4 to 1 of f of x equal to?
Just -2, or just 2.
Just 2.
No.
So he said the integral from 4 to 1 of f of x with respect to x is equal to negative the integral from 1 to 4 of f of x with respect to x. We know what the integral from 1 to 4 is. It's -2. So this is -2, which is equal to 2. Good?
Yeah.
Okay. Let's do a more complex one.
Okay.
We're going to look at the integral from -1 to 1 of 2f of x plus 3h of x.
Won't that just be 6 times 5 plus 7?
6 times 5 plus 7?
Do I have that right?
Well, I don't know. So
You have to
let's
take out
start
the
with.
functions first, right?
No, because you have to separate them. I don't. Can you
So let me rewrite this whole integral a way that we can rewrite this whole integral. First off, we can split it into 2 integrals,
Yeah.
and then we can pull the constant out of each integral.
Oh.
Yeah.
So this is the same as 2 times the integral from -1 to 1 of f of x with respect to x plus 3 times the integral of negative 1 to 1 of h of x with respect to x.
Then you can just plug 7 and 5 in.
And then we can just plug 5 and 7 in. And what do we get?
10 plus 21.
31.
Yeah.
Okay, now I did something weird in my head. 31, you're right. I read those both as 7. 31. 10 plus 21. Okay. So, calculate that one. Now let's calculate this one. What's the integral from negative 1 to 4 of f of x with respect to x?
Well, we can split it into the integral.
A to C and
Yeah,
So it's negative.
A to B and then B to C.
so it's negative 1 to 1 of f of x with respect to x.
With respect to x.
That's plus the integral of 1 to 4 of f of x dx.
Just 3.
Good? Now, I don't know if we've come across this yet, but how do we get negative areas when we calculate the area under a curve? One way is calculating the area backwards, going from B to A rather than A to B. That will give us a negative. But negative area will also be area underneath the x-axis.
So if you're a negative function,
Oh, so you need to know what the functions do.
Yeah, so let me give you a really quick example. Let's say I'm just doing an integral of the function x, which is just a vertical line, right? And let's say I do it from negative 1 to 1. So here's negative 1, here's 1. And I calculate the area. All this area is going to come out negative. All this area is going to come out positive. And if I calculate that integral, I'm actually going to get 0. So areas underneath the x-axis come out negative.
Why don't you find just the absolute value of it then?
You could. There's no problem with that.
What's more important then to find?
Huh? It depends on what you're interested in. Maybe you want this to count as negative, maybe you don't. A lot of cases we do want areas underneath the curve to count as negative. And we just want to know the total area above the curve.
Why is that?
The same reason that sometimes we want to know velocities rather than just speed. And we want to know displacement rather than distance.
That makes sense. Okay.
It's about what you're interested in. So this is going to be very much related to, were you after velocity or were you after speed? Velocity, we want that to count as negative. Speed, we don't. Speed's always a positive value.
Yeah.
So it just depends on what you're interested in.
Okay.
So depending on your problem, you'll know how you want to count. Just keep in mind that with how an integral is, because remember, the integral gives us height times width a bunch of times, right? What's the height of this point? Negative 1.
Negative.
Times a positive width gives me a negative number. So with how the definite integral is defined, remember that we were just using area to guide our intuition for an integral. An integral is not area. An integral is that exact thing over there. It's just really useful to calculate an area.
Because we're looking at the infinite amount of rectangles, right?
Yes. So definite integral, it's that exact thing right there. Not once do we use the word area. We just use area to guide our intuition.
That's interesting.
So it's not necessarily area in the way that you might think. The same way that if we calculate this integral, we get 0. But you see how we could use an integral to calculate that area.
Yeah.
We'd calculate one integral from here to here. It would spell a negative number, but we just take the absolute value. And then we could calculate the integral from here to here. And we could easily get that area if we want to.
So an integral is not area. It's a
No,
sum.
an integral is the limit of an infinite sum.
Okay. I think I get it now.
In the same way that derivative isn't really slope. We just use slope to guide our intuition for a derivative. You can calculate derivative of a lot of things.
Yeah.
Okay. Anyways, okay, so we did all these. So now let's come and look at that example. Can't leave myself any space for that example. Guess we'll write down here. Example. Show that the integral from 0 to 1 of the square root of 1 plus cosine of x is less than the square root of 2.
Okay.
How on earth are we going to do that?
Well, we can map out the function first, right?
Draw a picture of it?
Yeah. that
Sure.
will.
Let's draw a picture of it. So we're going from 0 to 1. We'll do 1, 2 like that. What does this function look like? When you plug 0 into it, what do you get?
Root 1 dx.
So 1.
What's cosine of 0?
Oh, you get
What's the x coordinate at 0?
1.
1.
1. So what do we get when we plug in 0?
Root 2.
You get root 2.
Root 2, which is somewhere up here. There's root 2.
Yeah.
So we'll start that right here. What do I get when I plug in 1?
That's when you get 1.
1. And so this function curves down like that to 1. Roughly. There's a rough picture. Not sure exactly what it looks like. Okay. What are we trying to prove?
That's less than or equal to root 2.
That the area underneath that curve is less than or equal to the square root of 2.
But root 2 is your max, right?
Root 2 is your max.
Yeah.
Root 2 is the area of the sink.
And that's going to always be greater than your integral.
Right, so I know that f of x, if we call that thing f of x, I know that f of x is less than or equal to root 2 on 0 to 1. Right?
Yeah.
Therefore, using property 7,
Property 6.
7,
Oh.
if f of x is greater than or equal to g of x on some interval, then the integral of that one is greater than or equal to the integral of this one. Right?
Oh, and your g of x is just the constant, right?
Yeah, we didn't calculate what a constant is in general, but we know what it is. So what is the integral in this picture? What is the integral of the square root of 2 with respect to x? On this interval from 0 to 1.
Root 2.
Root 2.
Sorry, I'm lost.
What is the area of this rectangle? Look, let's create a function here. So here's f of x. G of x, we'll say, is now equal to square root of 2. Right? There's our g of x function.
Okay.
Plot it. It's just a straight line. It's constant. Square root of 2, right?
Mm-hmm.
What's the area underneath square root of 2 between 0 and 1?
Just root 2.
Root 2. Okay, so the integral of root 2 from 0 to 1 is just equal to root 2. And I know that the integral of this thing has to be less than or equal to the integral of root 2, which is root 2. So this is less than or equal to that. You follow the thinking there?
Yeah, I see it.
Good? Okay. So it just so happens that on this interval, the integral of root 2 is root 2. So don't get confused by the fact that root 2 is g of x and root 2 is the integral of g to x from 0 to 1.
Oh, so a constant, an integral of a constant is never just the constant, right?
No.
Never.
No, because think about if this went on to 5.
Yeah, it'd be
What would the integral of root 2 from 0 to 5 be?
5 times root
5
2.
root 2.
Yeah,
So no, it's not just a constant.
okay.
It just happened to be 1 root 2, which is the same thing as root 2 in our example. So don't let that fool you, and we'll calculate the integral of constant in general. Okay. So we did that example. That example made sense. Let's go on to the next thing, definition. Let f be integrable and positive, so that's supposed to say, on the closed interval a, b.
So it doesn't go negative.
So
That's-
no negatives, no getting below the x-axis. And we're assuming b is a number greater than a. Then the area A under the curve y equal to f of x over AB is defined to be the definite integral. So now we have a definition of area. So notice that we use integral to define area.
Yeah, but if it's area, does it have to be positive then? Why not just find the absolute value of it?
Well, the absolute value of a function, that makes the whole function positive. So it works.
Oh, I see.
You don't do the absolute value of the integral. You do the integral of the absolute value of the height times the width.
Oh, because the integral is the integral.
So here's what you calculate when you want, if you want, of course, everything to be above the x-axis. You calculate the limit as n approaches infinity of the sum k equal to 1 up to n of the absolute value of f of a plus b minus a over n times k and absolute value times the width. So that's where you insert your absolute value. Which then makes this function, when you take the absolute value of it, is now positive, which now gives you an area that fits the definition.
I see.
Okay, so let f be integrable and positive on the closed interval AB, then the area A under the curve y equal to f of x over that interval is just a definite integral. And so now we have a definition for area. So
And that's the definition of area
that's the definition of area under a curve.
under a curve.
Yes.
Okay, yeah.
Which is the intuition we've been using to take guidance this whole time, but now we actually have a definition.
Okay.
So you use integrals to define areas.
Okay.
Alright. Next. Let f of x equal x. Find the integral from 0 to some point b of f of x with respect to x, where b is assumed to be a positive number. So now we're going to calculate an integral, and we're going to calculate an integral by hand, going back to stuff we were doing last week.
Okay.
So let's set up the integral. Always the hardest part. Set up the integral. We'll start by just setting up our Riemann sum. We'll take our limit when we're done with the sum. You with me?
I think, yeah.
So let's set up our Riemann sum. So we're going to do the sum from k equals 1 to n of f of our right-hand points times our width. That's our formula, right?
Mm-hmm.
Now, that's just our formula to help us think. Now let's write out our sum for this thing.
Okay.
You with me? Okay, so we're still going to do the sum from k equals 1 to n. And now we're going to do f of, what is our right-hand point going to be?
Negative b. Oh, b, sorry.
What is our a in this?
0.
0.
Oh, I'm looking at your note, sorry.
Oh, yeah, ignore the note for a second.
Yeah, it's gonna be,
In fact, we don't care about that note anymore. We already had that exact conversation about negative areas. So, what is it?
0.
A is 0. Now what's the whole thing? Tell me what to write.
a is 0?
Yeah.
But you said your right hand. Your right hand point is b, right?
I'm using the right-hand point of each rectangle to calculate my height.
And that's 0?
No, the A is 0.
But that's your far left hand. Okay. You have your right hand point and your left, right?
Okay, we are losing track of things here. We've got our curve, right?
Mm-hmm.
Here's A, here's B. Good so far.
Yeah.
Okay, we're going to use the right-hand points to calculate the heights of our rectangles. So when I calculate my first rectangle, I go to the height at the right-hand point to figure out that rectangle. I go to the height at the right-hand point to figure out that rectangle.
Yeah, I see what you're doing.
Okay, that's what we mean by right-hand points. We are not saying that we're using B every time. We're using the right-hand points. That's terrible. With me so far?
Mm-hmm.
So what are the coordinates of the right-hand points? What's the coordinates of this point?
Just whatever that point is minus a.
We're trying to find that point. We can't use that point to find that point. What is the coordinates of this point?
What?
What's the coordinate of this point?
Just
A. Okay, so we have to go A to get to this point. How far do I have to go to get to this point?
A plus your n.
A plus that width.
Yeah, plus the width.
What is that width if we
Delta A.
evenly divide it? So if I evenly divide this up into n pieces, what is the width of one of them?
B minus A over.
B minus A over. That's right.
B minus a over n. So that is the coordinates of this point. What about the coordinates of this point?
You're having two of the widths.
Yeah, 2 of the widths.
Okay, so what about for the cape rectangle now? Not the third one, but the cape one.
Okay, I see where we're going.
Okay. It's giving us the right-hand points.
Yeah.
All right. So this is the right-hand point.
Okay.
So what is our right-hand point for our specific function now? Notice that we're going from 0 to b.
K times B over.
0.
K times b over n. Our total distance is b. We're dividing that up into n pieces. We're starting at 0, and we're going to do it k times to get to the k rectangle. Right?
Yep.
Okay.
Times B over N.
Times b over n. Perfect.
Okay.
Okay. We're simplifying now. We know what this function is actually equal to. What's f of k times b over n?
F of K.
We know what our function f is. Huh?
Oh, F of X is just X, so it's just K times B over N.
Right, so it's just k times b over n. So when we do the whole thing, we get k times b squared over n squared.
Okay.
Follow that?
But you can take your constant out, right?
Yep, we can take all our constants out. So this is equal to b squared over n squared times the sum from k equals 1 to n of k. The only variable we can't take out is k, right?
Yeah.
What is the sum of k from 1 to n?
We sum of K from 1 to N.
What's 1 plus 2 plus 3 plus 4 plus 5 all the way up to 1,000?
The sum of 1,000.
What is it? Calculate it. Tell me what the sum actually is.
I don't remember how to calculate that.
It's n times K.
It's n times n plus 1 over 2.
Yeah, that's right.
Right?
Oh.
And then we have K squared and K.
Okay, there we go.
Yep.
So we have b squared over n squared times n plus 1 all over 2. Look, you should be able to come up with that formula pretty quick on your own.
Yeah. Yeah, we should.
Yep.
Okay.
Okay. So, a little bit more simplifying, I guess. This is equal to b squared times n squared plus b squared times n all over 2n squared. Well, we'll keep this 2 separate terms, actually, because we're going to be calculating this limit. So that's what the Riemann sum is equal to.
Okay.
But to get the integral, I need to take the limit as n approaches infinity of the Riemann sum. Right?
Well, can't you simplify that further?
Oh, sure.
Taking out the n.
Right?
Yep.
Okay, so now the integral from 0 to b of x with respect to x, when we actually calculate the limit, what do we get? What's the limit as n approaches infinity of this thing?
It's B
Well,
two
as it
over
approaches
2.
infinity, then the right hand just goes to 0, right? So then it's just B squared over 2.
B squared over 2. That's it.
That makes
You
sense.
just calculated it.
So we don't need to do this stuff with specific points. If you see
The
what I'm
area is
saying.
between 2 points.
Yeah, I'm saying we don't need to know whether the point is 5 and 6. All we need to know was that was 0 on B and what f of x was, right?
Yeah, now for any b, you can calculate the area really quick.
Yeah.
So now check this out. You can do crazy math now. If I say we've got a triangle with a slope of 45 degrees, so this is just x, right? Here's my function f of x is equal to x. You with me?
Yeah.
Okay.
And we want to calculate the area now from 0 to 6. What is it?
36 divided by 2, which is
You sure?
18 times 2.
We can do a quick little sanity check. Turns out you should already know how to calculate this area. What's half the base times the height? It's just a triangle.
What's the height?
6. It's a 45 degree.
Oh,
It doesn't
which
look
is
like it.
18.
Which is 18. Yeah, it's just a triangle. Isn't that amazing? You can now calculate the area of a triangle.
So,
So that's 6, that's 6. You just
But we
calculate
already
the
knew
area.
that before.
Yeah, you already knew that. You just came up with the area for calculating a 45 degree triangle. If we call this side length b, and we call this side length b, what's the area? B squared over 2. Yes, you already knew it. This is the point. Calculate an easy integral where you already know the answer. I'm trying to get you
Okay.
to think about, does that answer make sense?
Yes.
Okay, that's what I want you to do. I want that connection. I don't care that you know a formula. I want that formula to appeal to your intuition. Ah, yes, this makes sense.
Is that the case for all triangles or just 45 degree angle?
No, that's just this function.
And how about other triangles like equilateral and stuff?
Well, you'd have to come up with a function to represent the triangle. This is also assuming a 90 degree triangle.
Oh.
This will give you the area under a curve. If you can come up with some clever curve that captures the area you want, then you can calculate that area.
I see.
Okay, so let's think about this for a second. We're going to try something a little bit different now. So b was this point, right?
Mm-hmm.
Now let's say that we were doing this function and we weren't going from 0 to b, but instead we were going from a to b. So I don't want this whole area. I just want this portion of the area.
Wouldn't it just be?
It would be the whole area minus this area, right?
Yeah.
So, if I were to ask you now, what is the integral from a to b of x with respect to x, you now know it's equal to
b squared over 2 minus a squared over 2.
b squared over 2 minus a squared over 2. Perfect.
Oh.
The whole triangle minus the smaller triangle.
Minus. Okay, I see that. Yeah.
Make sense? Okay, so there's our first integral that we have a formula for. If I ask you to calculate what's the integral from a to b of x with respect to x, you now know that this is b squared over 2 minus a squared over 2.
Yeah.
Good?
Mm-hmm.
All right, let's look at the integral of a constant.
Okay.
Okay, so we'll calculate our Riemann sum for a constant function. See what this is. The integral of constant. So our Riemann sum, we're going to have the sum from k equals 1 to n. Our height is all we see. And our width is b minus a over n.
Okay.
Setting up the Riemann sum for this function. You with me?
Yeah.
Okay. Let's simplify.
Okay.
We can pull the c out, right?
Yeah.
Oh, yeah.
We can also pull the b minus a out, if we think about that as one term. Maybe I'll do this one step at a time, just so you don't lose it. I can write this as b minus a times 1 over n. Same thing, right?
Yeah.
So I can also pull the b minus a out.
Mm-hmm.
So this is equal to c times b minus a times the sum from k equals 1 to n of 1 over n. What is this sum?
0.
Add up a bunch of positive numbers and get 0? That doesn't make sense.
Aren't you? Oh, you're not trying to find the limit.
Just
Let me set up a special case. Let's do the sum from k equals 1 to 100 of 1 over 100.
1 over 100.
You mean 1 over n?
I'm doing a special case where n is 100. If I add up 1/100th 100 times, what do I get?
1.
1. If I add up 1/n, I do 1n plus 1 over n plus 1 over n plus 1 over n times. What do I get? 1.
Okay.
So the whole thing is just c times b minus a. You with me?
Yeah.
Finally, take the limit as n approaches infinity of that thing.
It's just that thing.
Good? And notice this is what we did when we did our integral of the square root of 2. We did the square root of 2 times 1 minus 0.
Yep, I see how that works.
Makes perfect sense. Let me just draw one more picture, which hopefully makes you can just scream out that equation without even thinking about it.
Okay.
So here's c, we've got a constant function. So here's c. I'm looking for the area underneath c between a and b. What's this distance?
B minus A.
What's this distance?
C.
And so the total area,
C times b minus a.
Yep.
right?
Yes, sir.
Okay, so all of this makes perfect sense.
Yeah.
You now know how to calculate every integral. We don't need to worry about it anymore.
Yeah, we're naturals.
Yeah, you're naturals. Okay, next. Moving over to this board. Have to save that for philosophy last night. Okay. Conversation that we've already had, but let's remind ourselves of the conversation. If I have some function from a to b, and I already know that the area underneath the curve is a, what's the average height of the function? What's the average height the function reaches here?
A times b minus a. Or,
You're trying to remember what you said instead of thinking about what makes sense.
yeah.
How could I get the average height of that function?
B minus A divided by. No.
A divided by b minus a.
The area divided by the width should give me the average height of that function. Right? Area is height times width over and over again added up. Divided by the total width should give me the average height of the function.
Okay.
Make sense?
Yeah.
Okay. So now, let's define what we mean by average height. We're going to say that exact same thing. Don't get confused by notation. Turns out this is notation for average height. It's not what I used last time, sorry. So the average height of f on the interval beta a is equal to the area divided by the width.
Yeah. Okay.
Make sense?
Mm-hmm.
This is area. This is divided by the width. So, makes intuitive sense?
Yep.
Okay, so let's use it. Find the average height of f of x equal to 4 minus x squared from negative 2 to 2.
So,
Now we keep coming across this equation, so hopefully it's starting to click in your head what this is.
two.
No, that's that's a bunch of points. It's not a number.
B minus a is 4.
Let me rewrite this another way.
That's right.
So what is it? Tell me what shape that is.
Isn't that a triangle?
We have gone over this so many times.
I'm sorry.
It's the equation of a circle with radius 2.
That's the equation of a circle. Isn't that the Pythagorean theorem?
That's how it should be screaming to you, equation of a circle. Look, pick a point on the circle.
Yeah.
Say it has coordinates x, y.
Okay.
This is, then I know that x squared plus y squared gives me this distance, right?
Mm-hmm.
Or gives me r squared. So this is r, that's my point x, y. So I know r squared is equal to x squared plus y squared from the Pythagorean theorem. On a circle,
Yeah.
right? If I give my circle a radius of 2, then I know everywhere on the circle x squared plus y squared is equal to 4.
Okay.
Okay.
So we pick this point on the circle. This point on the circle has coordinates 2, 0 if this is a radius of 2. A squared plus a squared gives me 2. If I pick the 45, its coordinates are root 2 and root 2. That squared plus that squared gives me that squared. Anywhere on this circle, take its 2 coordinates, square them, add them together, gives me the radius squared from the Pythagorean theorem. Okay,
Okay.
equation of a circle.
Okay.
Okay, so now we've only got the top half of a circle. This is just the top half. Because really, if I go from here to here, that's fine, but when I go from here to here, I have to say y is equal to plus or minus the square root of that. We only have the positive case. So we have the top half of the circle. Y is always positive. We're not looking at any negative y's.
Okay.
Top half of the circle. Only positive coordinates and 0. So we are looking at a really rough picture. Some top half of a circle with radius 2. Radius 2, 2, 2.
Isn't that just an upside down parabola?
No, no, no. That's my picture line to you. Parabolas are not circles. Parabola looks like this. A circle is a circle.
Oh, yep.
Okay. So, don't let my picture lie to you. That's a circle, even though it doesn't look like one.
Are we trying to find
Calculating the average height of this thing. What's the average height of all these points? If I were to take all these points and average out their height, what would I get? How do we calculate the average height? The average height, the average of f, is equal to what?
Oh, would be minus A, would be minus
The area divided by the base.
Yeah.
What's the area?
Area of circle is 2 pi r.
That is the circumference of a circle. You have to be squaring something because the dimensions come out squared. Area of a circle.
Pi r squared.
Pi r
So
squared.
it's
Pi r
4.
squared.
Okay. So it's what?
Pi 4. Or 4 pi.
How much of a circle do we have?
We have half of it, so it's divided by 2.
Okay, area. 2 pi. What's our base?
4.
4.
2 pi. Where'd you get 2 pi? What happened to the r squared?
R is.
What's r squared?
R is 2.
4.
And we only have half a circle.
So you had to divide that by half.
But where'd you get divided by 4?
Okay.
That's the.
Draw a circle with radius 2. What's the area of the circle?
Pi r.
Pi r squared.
Pi r squared.
That's what I
Which
said.
is?
4 pi.
Okay, what's the area of half that circle? Just this half.
2 pi. Okay.
Okay.
I get that, but I'm asking where you got the 4.
B minus A.
The width. We take the area and we divide by the width. What is the width?
But b minus a isn't exactly 4, because it's 2 minus 2.
2 minus
2 minus minus 2.
Oh, sorry. I see. Okay.
Remember, it always gives you the distance. If your
Yeah.
intuition and your equation that you have in your head are going against each other, follow your intuition, not the equation. You know the base is 4.
Yeah.
If the equation is telling you something different, you're misusing the equation. Sanity checks. Make sure it makes sense. Okay, so there's our average height, or pi halves. Pi halves is the average height of this function on that interval. Isn't that crazy that we can calculate that?
No, because it's pi halves times. Oh.
It's just pi halves.
I see what we're doing now.
Guaranteed. That is the average height. The average height of all these points, pi halves. So if I give you a ton of data points, and it turns out that those data points mimic the top half arc of a circle, and I say I need you to average up these data points for me, you can say it's pi halves.
Okay, that makes sense.
As long as the radius is 2.
Well, yeah, for this specific scenario.
Do you have another example for us?
You want to calculate another average height?
Yeah.
Okay.
Yeah.
But it has to be shaped so you can easily calculate the area of, like a circle.
Well, why not just go and do the...
We don't have integrals yet. Remind me when we can calculate an integral and we'll come back and do another one. Because I do like an upside down parabola, but you don't know how to calculate the area underneath the parabola.
Haven't we been calculating integrals?
Oh, I'm not going to do it by hand. I mean, when we do the antiderivative.
Oh, so you get lazy.
Yeah. Let's see, you do one. All right, I will let you calculate the area underneath the parabola if you'd like.
Okay.
We'll do that at the end of class.
Okay.
We won't make a recording of that. Okay. So, okay, we did this one. Nice, simple example, right? Calculate the average height. Okay, theorem. And we got to prove this thing. So this is called, oh no, this isn't it yet. Sorry, I thought we were at the fundamental theorem of calculus. If S is continuous on the closed interval AB, then there exists some point C in AB such that f of C is equal to the average height. Okay, let's make intuitive sense of what this is saying. So, we got some function. It's a continuous function.
Okay.
That function has an average height on this closed interval, right?
Does a continuous function always have an average height?
Yeah, because we can calculate on a closed interval AB always has an average height.
How about on the entire?
No, because it could shoot off to infinity.
Oh, I see. Okay.
But on a closed interval AB, yes, it always has an average height because we can always calculate the area, and area divided by the base gives us average height by definition. So our definition of average height. With me?
Mm-hmm.
Okay, so this function, whatever it looks like, it has some average height it achieves. Whatever it is. What are we proving? I am proving that always and forever there exists some point in here C such that the height at C is the average height.
Okay.
So there has to be some C in this interval such that C is equal to the average height. So if f is continuous on a closed interval AB, then there must exist some C in that closed interval, A to B, such that the height at C is equal to the average height. That's what this is saying.
Yeah, that makes sense.
Makes perfect sense, right? Okay, so let's prove this thing really quick. I won't rewrite out what we're proving. We'll just start. One, let f be continuous on the closed interval A to B. 2, let's see. Then I know that m times b minus a is less than or equal to the integral from a to b of f of x dx is less than or equal to, I didn't specify what little m and big M were. Let f be continuous on AB, comma, let little m equal the min of f on AB and big M equal max of f on AB. You with me with little m and big M? Same things we've always been talking about. Then little m times b minus a is less than or equal to the integral is less than or equal to big M times b minus a. We already proved that, right? That was the proof we did over there. I told you we'd be using it later in the class. Good so far?
Yeah.
3. Then, little m is less than or equal to 1 over b minus a times the integral from a to b of f of x with respect to x is less than or equal to big M. I divided everything by b minus a.
Why are you dividing everything by b minus a?
Well, first off, see what I'm trying to prove. I'm trying to prove that there exists, where are we? Up here. I'm trying to prove that there's some point C such that the height at C is equal to this thing. I definitely need this thing to show up.
Okay. But how do you get c in there? Just say that it exists.
No, you'll see right here. But you're good with that step. That step makes perfect sense. What is little m?
Your minimum.
It's the minimum height the function reaches on the interval a to b. So whatever my function does from a to b, I know it reaches, here's little m, and here's big M. Right?
Yeah.
Okay, so I know that f is a continuous function, and that f at some point is little m, and that f at some point is big M. So, 4. Then, by the intermediate value theorem. What does the intermediate value theorem say? It says if the continuous function reaches this point and this point on some interval, it reaches every point in between.
Yep.
Here's a point in between.
And so you're just going to call that c?
So then by the intermediate value theorem, there exists C in AB such that the height of that point is equal to some point in between, namely that. And we're done.
Yep.
Make sense?
It's demonstrated.
And thus it is demonstrated. And now we know what it means to demonstrate. Good?
Yeah.
Any questions on that?
Nope.
Alright. So that's that proof. Next, what are we doing? Prove if f is continuous on AB, and that if the integral of f of x is equal to 0, then there exists some c where c is equal to 0.
Isn't that just using that definition?
Is that
Using
one-
that theorem? Yes.
Theorem, yeah.
Yes, yes, yes. So maybe I won't do a proof of this, I'll just make it make sense. So I know that, here's what I know. I know that the integral from a to b of f of x dx is equal to 0. That's what I'm given.
Okay.
So here's what we're proving. I'm going to prove that if the integral is 0, then the function had to equal 0 somewhere. Right?
Yeah.
Yeah.
And notice that there's a couple ways that we could get an integral equal to 0. First off, I could just have the height of my function always 0. Right? Another way I could do it is I could have as much positive area, as much area above the x-axis as I have below the x-axis. So they perfectly cancel out and we're left with 0. But in order to get from positive area to negative area, I have to cross the x-axis. And where I cross the x-axis, the height of the function is 0. So that's what we're basically proving.
Okay.
If your integral is 0, your function has to cross the x-axis, where the height is 0 somewhere. Right?
Mhm.
So, the integral is equal to 0. Then that gives me that my average height of f is equal to what?
Your average height is 0.
0. How'd you do that?
Because you have negative and positive, and it goes back.
How do we calculate average height? Area divided by,
Width.
sure, base, but yeah. What's the area?
0.
0 divided by b minus a
Is
is equal to?
0.
0. So my average height is 0.
Yep.
Okay, previous theorem. Your function achieves the average height at some point.
Yep.
We're done.
Okay.
Make sense? Okay. So now notation. Notation, notation, notation. This is common notation. Let me just write it out. Well, we have it right here. If I have a little function, little f, and I want to talk about its integral up to some point x, we often represent that with big F of x.
How do you know? Oh.
So you're saying if you want to talk about the integral of a function, then you can represent that as just...
Yeah, if I see big F of x, as a general rule, we reserve this as notation for, that's the integral from some number a to x of some function.
It's always to x though, right?
Yes, that variable and that variable are the same. It's the integral up to some point, the area out to some point.
Is it always t?
No, this one here doesn't matter.
Yeah.
So what does this give me? If we have some function, f of u is the way I have it written there. So here's f of u. This is f of u. Here's some number a. And I want to know the area from a to some value x that might change, some variable distance. So I want to calculate the area up to x. F of x gives me that area.
Does it work if x was like 3?
This is just notation.
I mean, if you didn't know what x was, could you just substitute it?
Sure, f of 3 is the integral from a to 3 of that function, the area up to 3.
Okay.
So f of x is just basically rewriting a.
This is just notation for this. The same way that if I say f prime of x is equal to, you know what, this is shorthand for a derivative. Derivative of what? I don't know. Derivative. It's just notation. This is just notation. It's the integral of a function from a to some point x. What function? I don't know. Just some function. Take its derivative. Find the function. Some function. It's just notation so far.
Gotcha.
Okay. So it's notation for this thing right here. Keep that in mind as we do these next things. So now we're going to prove the first fundamental theorem of calculus. Well, it has two parts. We're going to prove the first part of the first fundamental theorem of calculus.
What? Okay.
This thing. If f is continuous on AB, something like this, here's f. If f is continuous on AB, then the derivative of this thing, so we have, let me write that up here, f of x is equal to the integral from a to x of f of, I did u over there, u du. So f is some continuous function, that's all I know about it, from a to,
X.
from a to b, x is some point in between
Oh, I see.
a and b, so here's b, get our whole picture up here. X is some point in between a and b, because we can only do integrals where the function is continuous. We only know it's continuous from a to b, so that's all we can use for short.
Okay.
Okay, so what am I going to prove? I'm going to prove now that f prime of x, the derivative of this thing, which is the same thing as the derivative of this with respect to x. Notice with respect to x, not with respect to u. Is equal to f of what you get when you plug in that x.
Why isn't it just f of u? Why is it equal to f of x? Like, why is it with respect to x instead of respect to u? Your derivative.
Here's what I'm going to prove.
Oh, you're proving this?
Yes, this will be something that we prove.
Oh, I think if you do the proof. Then
I am proving, because what is f prime at x? That is the change in this function at x, right?
The derivative of the area, right?
Sure.
Okay.
So f prime of x is the change in this function at x. This is the area function.
Yeah.
How much is the area changing at exactly x? How much area do we add on here at x? We're saying, how much is it changing? It's changing by the height of the function. If the function is tall at x, we're increasing the area a lot. If the function is small at x, we're increasing the area a little bit at that point.
Okay, that makes sense.
So we're proving that the change in area is the height.
So why is this the most important theorem?
Because notice what else it's saying. When you take a derivative of an integral, you're left with the internal function at a point. Or in other words, derivatives undo integrals. Which is going to tell us that an integral is somehow an antiderivative.
Oh, and then we can
We're
start
working
calculating.
up to using antiderivatives to calculate integrals.
Okay.
Okay, so that's what we're going to prove. Put a pin in it. I want to do some examples first to get a sense of using this thing, because it's not intuitive, because you're going to be confused by the dummy variables at first, which is fine. But you also got to get past it. So we'll prove that, but first let's do some examples. So example, find dy dx if y is equal to, so I'm going to say y is equal to the integral from a to x of t cubed plus 1 dt. My job now is to find dy dt, or dy dx, sorry, the derivative with respect to x.
Okay.
So I'm looking for the derivative with respect to x of this integral. And what does that equal?
Just t3 plus 1.
It equals what you get from your function when you plug x in there. So what is it?
X cubed plus 1.
X cubed plus 1.
Okay.
The height of the internal function at the point x. That is how the function is changing at that point.
Yeah.
Make sense? Let's use it again. Okay, this time we'll say y is equal to so we did this one, let's look at this one. Y is equal to the integral from x to 5 from x to 5, make sure I don't lose it, of 3t times sine of t dt. Good? Now, we don't like where the x is. What do?
Negative.
Make it negative. So this is also equal to negative the integral from 5 to x of 3t sine of t dt. Right?
Yeah.
Okay, now we're looking for its derivative with respect to x. So the derivative of y with respect to x is equal to the derivative with respect to x of the integral from 5 negative the integral from 5 to x of 3t times sine of t dt, which is equal to what?
Negative 3x times. Do you do cosine, or is it just sine of x?
Plug it in. That's it.
Okay.
Nice and simple. Right?
Yeah.
Okay, more complex one. Here's where we're really going to get you. Y is equal to the integral from 1 to x squared of cosine of t dt. All right, now we're stumped. This does not fit our definition. We have an x squared there. We only have an x there.
Would you just have to square root the whole thing?
No, that doesn't. No. You can't square root to get rid of that. So here's what you do when you have something that's not just an x there, or just a u there, or just a something. I'm going to say, let u equal x squared. You with me?
Mm-hmm.
There's nothing wrong with plugging in a different variable, is there?
Don't think so.
No. Nothing wrong with that. So now y is equal to the integral from 1 to u of the cosine of t dt. Right? But what are we looking for? We are trying to figure out what dy dx is. And now we have u's.
Okay.
Well, dy dx is also equal to the derivative of y with respect to u times the derivative of u with respect to x.
Chain rule, right?
Yes.
Okay.
Now let's look at the derivative of y with respect to u. What is y? Y is this whole thing.
Mm-hmm.
So we're looking at the derivative with respect to u of y, the integral from 1 to u cosine of t dt. So that's just the derivative of y with respect to u times, so maybe put brackets around this whole thing so you don't get confused by where our integral is, times the integral of du dx. With me?
Yeah.
Okay, and now that's equal to, okay, now we know how to work with this thing. What is the derivative of this thing with respect to u?
Just cosine of u.
Cosine of u. Right?
Yeah.
Times du dx. Right? But what was u?
X squared.
So this is cosine of x squared times, what's the derivative of u with respect to x?
dx.
What's the derivative of u with respect to x?
2x.
2x. Or in other words, 2x times cosine of x squared is where we write it. Make sense?
Yeah.
Let me pull up the book just to make sure I'm not making mistakes on any of this.
Sure hope not.
I sure hope not as well.
Otherwise, it'd be pretty rough for you, Peter.
It'd be what?
Pretty rough for you, Peter. Trying to do some homework and do it wrong.
Even if I do it wrong in class, you'll still do it right on your homework. 2x cosine of x squared. Okay. So, no major mistakes.
Okay.
All right, let's do the next one. And see the pattern there that we were able to do. We did a u substitution for that thing, and it makes out we were calculating this.
Yeah.
Same thing we were doing before. The derivative of the outside multiplied by the derivative of the inside. If you think about this as what we're plugging in.
Okay.
Make sense?
Yeah.
So we're going to try and do the next one all in one go.
Okay.
All in one go. Yeah.
All in one go.
Yeah.
Easy.
See if you can just see it. We can spell it out afterwards if we're getting stuck on something. So let's just see if you can see it all in one go. And you can just say what it is. And I erased your formula. You also have it right here. Okay. So we are looking for the derivative with respect to x of the integral from 1 plus 3x squared to 4 of 1 over 2 plus t dt. What's that equal to?
Well, first you want a negative.
So we know we're going to have a negative because we're going to have to flip those.
And then it's just 1 over 2 plus x.
Plus what?
1 plus 3x.
1 plus 3x squared.
1 plus,
3x.
yeah. 1
Because
plus
it would be 2
3x.
plus u, but our u would be
So it's 3.
Okay.
Multiplied by 6x.
6x.
Wonderful. See, that wasn't so bad. Which,
Yeah.
simplify it for me.
6.
Negative 6x.
2x over 1 plus x squared.
Negative 2x over 1 plus x squared. And let's make sure we didn't make a mistake. Negative 2x over 1 plus x squared. Good?
Yeah.
Not so bad? You need a break? Alright, I see I am the clock. Let's go ahead and take a break, and then we'll come back
Well, we have one more.
and do these couple proofs. Huh?
Couple proofs.
We have this proof, and I don't think I have everything up here.
No.
So, go ahead and take a break. I think we're almost done. Probably have another half hour. All right, so we used this first part of the fundamental theorem of calculus, which basically tells us that somehow a derivative undoes an integral. Right? Put my marker over here. So now, let's prove it. Let's calculate the derivative and see what it gives us. So I'm going to calculate this derivative and see if it gives me this. So one, just so we're clear, let f of x equal the integral from a to x of f of t dt. So we keep in mind exactly what f of x is. Remember, f is some continuous function on some closed interval a, b, and x is some point in between a and b.
Yeah.
So maybe state some of that. Where f is continuous on a, b, and x is in a, b. Okay, good?
Yep.
We're trying to calculate the derivative of this and show that it's just f of x, whatever that function is right there. With me? So, 2. Then, f prime of x. What is f prime of x? There's a lot of different ways we can write it. The way the author typically writes it was with the h. That's the limit as h approaches 0 of f of x plus h minus f of x all over h. I usually use a delta x in there, right? But same thing.
Yeah.
Limit of a difference quotient, change in height over run.
Where's the difference quotient?
Right here.
No, I get that, but I'm saying, why are you doing that?
That's the definition of a derivative. I'm calculating the derivative.
Oh, that's right. Okay, sorry.
Going back to the exact definition of a derivative. Don't go so in love with your formulas that you forget what a derivative is. Back to the basics.
Yes.
Back to when you were calculating derivatives by hand. You were calculating these limits. Good. Okay, so what's this equal to? It's just going to be hard for me to write it with the h in the denominator because f is that big integral thing. So I'm going to pull the 1 over h out, but not outside the limit. So we're looking at the limit as h approaches 0 of 1 over h times this difference, right?
Yeah.
And let's write out this difference. What is x plus h? That is the integral from a to x plus h of f of t dt minus the integral from a to x of f of t dt. Right? This is f of x plus h, this is f of x.
Okay.
Just from its definition there.
Yeah.
Good? Okay. So this is equal to the limit as h approaches 0 of 1 over h times, what is that difference?
Is h just a constant?
H is what's approaching 0. You can think about it as a really small number.
So
But it's a
just,
positive number.
just a number and a number slightly smaller than it, right?
X is going to be something like 5.
Yeah, that's
5
gonna be
plus
5
a teeny
plus
bit.
Teeny bit minus
Minus up to 5 leaves me what?
a teeny bit.
Small number close to 0.
Tell me the exact integral that equals. We have our sum rules for integrals.
Some rules.
Oh,
Just
a to
minus.
h. Right?
Not a to h. I take the area from here to here, if I take that area, and I minus that area,
You're left with
I'm left with,
x to x plus h.
right, left with the integral from x to x plus h of f of t dt. It's just our sum rules written a little bit different. Call this a, call this b, call this c. The integral from a to b plus the integral from b to c is equal to the integral from a to c.
I see it.
Therefore, the integral from a to c is equal, or the integral from b to c is equal to the integral from a to c minus the integral from a to b. So sum rules, just a little bit of transposing.
Okay.
Good?
Yeah.
Okay. So now, we're calculating this limit. Let me think. 3. Notice that this is also the average height.
Okay.
Yep.
We have area times base.
It's the average height of not the whole thing, right? Just that one.
Of that portion, from
Yeah,
x to x
that
plus h.
portion. Okay.
Yes, of that little teeny portion. So this is the average height of that little portion. So I know then there exists c in x to x plus h such that f of c is equal to is equal to 1 over h times the integral from x to x plus h of f of t dt. Right?
Mm-hmm. By definition.
Somewhere it equals the average height.
Yeah.
Then the limit as h approaches 0 of c is equal to
Just the
c always has to be between x and x plus h.
yeah.
If h gets closer and closer to 0, then x plus h gets closer and closer to
Itself. X.
x. So what does c get closer and closer to?
0.
X.
X. It's a number between x and x plus h. And if x plus h is getting closer and closer to x, and c is in between those two,
Oh. Yep.
c gets, there you go. So this is just equal to x, right?
Okay.
So the limit as h approaches 0 of c is equal to x. So 5, then, since I know that this is true, then the limit as h approaches 0 of f of c is equal to the limit as h approaches 0 of this whole thing. You with me?
Mm-hmm.
Taking the limit of both sides as h approaches 0. But f is a continuous function. So as h approaches 0, c approaches
X.
x. So f of c approaches f of x. It's a continuous function. What does it mean for a function to be continuous? I'll write it a little bit different than the way we're used to seeing it. It means that the limit, we're used to seeing the limit as x approaches c. In our case, we're doing it as c approaches x.
Okay.
So the limit as c approaches x of f of c is equal to f of x. That's the definition of continuity when that happens. I know f is continuous. So I know that as c approaches x, f of c approaches
F of X.
f of x. So this is just f of x.
Okay.
You follow that? This is a derivative. This is f of x. The derivative is equal to f of x.
Okay.
The derivative of big.
The
F
derivative
X.
of big F.
Yep.
Yep, remember that's what we're saying. The derivative of big F prime of x is equal to this, is equal to is equal to this. Here's its derivative, which is exactly what we have written here. Oh, I missed my 1 over h. Sorry about that. I had it there. I just missed it in this one spot. Limit as h approaches 0 of 1 over h times that. Okay. So this portion right here is just a derivative, and we showed the derivative is equal to f of x,
Which is what we're trying. Okay.
which is what we're trying to prove. Good?
Mm-hmm.
Okay, so that was our first theorem. We did the examples. Now let's do the second part of this theorem.
Where's the set? Oh, okay. You said.
Good?
Mm-hmm.
Okay. So the second part of this theorem now, which is right here. If f is continuous on AB and big F is any antiderivative, then the integral from a to b of f of x dx is equal to the antiderivative at b minus the antiderivative at a. So let's prove that one.
Can you give us some intuition for that first?
We will be using that equation 100 times after this. So
Okay.
So this is telling me how to calculate a definite integral now. It's saying, let's just use it once and get a feel for this. And then we'll do the proof. So now let's say I've asked you to calculate the integral. Now from 0 to 3, we won't do 0. We'll do 1 to 3 of 2x squared dx. Okay?
Okay.
That's what you're trying to figure out. How do you figure this out? We need to come up with the antiderivative for 2x squared. What's the antiderivative for 2x squared? 2x squared. When we take the derivative, we bring down the exponent and minus 1. Right?
Mm-hmm. Yeah.
So when we take the antiderivative, we add 1 to the exponent and divide by it. So the antiderivative of this is 2x cubed over 3.
Yep.
Notice when you take the derivative of that, it gives you that. So here's our antiderivative. So our function is saying, our theorem is saying, find any antiderivative of this function. Here's our function, here's its antiderivative. Here's a antiderivative. We could have also said plus 1, plus 10, plus 100, doesn't matter. Find any antiderivative. Typically we'll choose the one where the constant is 0, because that's easiest. Then this now is equal to, and I'll call this new antiderivative big F of x, right? So this was f of x. Here's big F of x, an antiderivative. So this integral now is equal to f of 3 minus f of 1.
So an integral is taking two of the antiderivatives and minusing it of a
One antiderivative, but it's different at 2 points.
I see what's going on. Okay. That makes a lot more sense.
So we plug it in. So what is this? 9 times 2 is 18 minus 2/3.
Minus 2/3. Yep.
Yeah. So what did we just find? We just found that if you draw this thing, 2x squared, so this thing shoots up really, really fast. Who cares? Shoots up really fast. The point is from 1 to 3, if you were to calculate the area under this parabola, it would be 18 minus 2/3. The area underneath this parabola from 1 to 3
Yeah, because it's big F.
is 18 minus 2/3. So this is the way that we actually calculate these things.
So this is like the simple way of doing it.
This is the simple way.
I gotcha.
We did not set up our Riemann sums. We did not take a limit as n approaches infinity. We just found one antiderivative and plugged in 2 points and took the difference.
So now that we know this already, like our 4.3 homework, would you still want us to go through all of that stuff?
If it tells you to do it that way, do it that way.
Okay.
If it says just find the definite integral, you do it this way. Okay, so that's what we're proving. We're proving that what we just barely did there works, and that we didn't cheat somehow.
Okay.
Good? Okay, so let's set this up. Let's see. 1. Let f be continuous on AB, comma, and let of f. How am I going to set this up? Since f is continuous, I know it does have an integral. So maybe let g of x be the integral from a to x of f of, I didn't really give it a name, did I? F of t dt, I guess, some dummy variable. So if I do that, then that gives me that the integral from a to b of f, I'm not going to bother with the t dt for a second, is equal to the integral from a to x of f plus the integral from x to b of f. Right?
Can you walk us through that?
Calculate the area from a to x, then from x to b, that's the same thing as a to b.
Yeah, but why the implication?
Oh, I'm going to write an equals here in a second.
Okay.
Is equal to a to x, that's going to be g of x, right?
Mm-hmm.
Minus, no, that's still weird. All right, let's look at the book for a sec. Get my footings. So, start out. Okay, so I'm on the right track with that. Let g of x equal that. Thus, if f is any antiderivative of f, so let's say 3, no, that f of x is going to equal g of x plus some constant c. So, we did this, we had this conversation already before.
Yeah.
We said if you have two antiderivatives of something, they can at most differ by a constant.
Mm-hmm.
You remember that?
Yeah.
So we're letting g of x be the actual integral of this thing. F of x is just any antiderivative. The point is we can use any antiderivative we want. We don't need to figure out exactly what g is. We can just use this f, and in the end it's not going to matter.
Okay.
So we're ultimately showing in the end that constant c just doesn't matter. You with me?
Mm-hmm.
So g is the integral of that thing. F is any antiderivative, and it's going to differ by from g by some constant c. You with me?
Yeah.
Okay. 4. Then f of b minus f of a is going to equal g of b minus c. That's this.
Minus c, isn't it? Plus c minus.
So far I just rewrote f of b. What's f of b? It's g of b. Oh, plus c, thank you.
Plus c, yeah.
Yep. And then we're going to do minus. When we plug in a, we're going to get g of a minus.
Plus.
We got to distribute this minus now. C.
Oh, I see.
Which is equal to g of b minus g of a.
And since they're the same, then
G of x, when we made this definition, here we should have done 0. It doesn't matter what constant we put there, but we'll put a 0 there,
okay.
just to help our intuition. Because this only depends on what the x actually is. But, well, we can define it however we want. That's fine. So now g of b, what is this? This is going to be the integral from 0 to b of f of t dt
Mm-hmm.
minus the integral from 0 to a of f of t dt. Yeah, it's actually just defined at the beginning. Okay, much better. So now what is that? If you know that b is a number bigger than a.
That's just the integral from a to b, right?
It's just the integral from a to b. Perfect. We're done. So it doesn't matter what antiderivative you use, because in the end the constants are going to cancel out.
Okay.
So let's see that really quick. We'll calculate an antiderivative, and we'll calculate an integral, and we'll use two different antiderivatives, and we'll see how it doesn't matter. And we'll just keep it simple. Let's do the integral from 0 to 2 of x dx. And see what this equals. Pick some antiderivative. I'm going to pick the antiderivative f is equal to, f of x is equal to x squared over 2 plus 7.
Okay.
Right? Take the derivative of this, you get this. It's an antiderivative. So we're saying that this is equal to f of 2 minus f of 0 for any antiderivative. Here's the one I happen to choose. Well, that's the same thing as 2 squared over 2, so 4 over 2, plus 7, minus 0 minus 7. And those constants go out. And so we're left with just the 4 over 2.
So your constant really doesn't matter.
Right. So since all antiderivatives differ by at most a constant, and since a constant ends up canceling out, it doesn't matter which antiderivative you use. Which is the point. So just always pick the antiderivative where the constant's 0.
Yeah.
Yeah, so if I would have just used this antiderivative, I'd get the same thing. That's the point.
I see what you're getting at.
So
Cool.
all you need to do is find an antiderivative, and now you can calculate a definite integral. Good? All right, let's do a bunch of examples now. Maybe I can just set this here. Readjust my camera. Okay, so let's really quick calculate a bunch of definite integrals now that you have the rules that you have.
Okay.
So we're looking for this integral. First, we need to calculate an antiderivative. What's the antiderivative of cosine of x?
Negative sign.
Negative sine of x. So notation now. When we actually go to calculate this, we say negative sine of x. There's our antiderivative. And then we put a vertical line to the right of it, or sometimes people use like a half parenthesis like that. I always use a vertical line. And then I put a 0 and a pi. And this means evaluate it at this point, then subtract what you get when you evaluate it at this point. Common notation. Anytime you see someone solving an integral, you're going to see this notation.
Okay.
So this just means plug in that point, then minus what you get when you plug in that point. Top to bottom. So now this is equal to negative sine of pi minus negative sine gives us plus sine of 0, which is equal to,
Sorry.
This is 0.
Sine of 0 is
did we
1.
mess up something?
Sine of 0 is 0. Right?
Oh, it is 0. Okay. That's because on this interval, cosine is positive for the first half and then negative for the next half. So it cancels out to 0. So if we look at the cosine function really quick, so we see what we're calculating. Here's pi halves. Cosine, let's look at our cosine function. At 0, it's 1, right? So cosine starts out right here at 0. You with me?
Yeah.
What's cosine when we plug in pi halves?
0.
What's cosine when we plug in pi?
Negative 1.
So this function looks like this. So we were calculating this area and subtracting away this area, which is why we got 0.
That makes sense.
So let's really quick see what would have happened if we would have just gone to pi halves, right?
Okay.
So if we were just going to pi halves, we just put pi halves there, which gives us the pi halves here. And what do we get?
You get negative 1. Or 1. Or,
1 plus 0.
but there's a negative sign.
I'm doing something weird. We're missing something so obvious it hurts.
Okay, that helps.
The derivative of sine is cosine.
Now it's just
The
We were
derivative,
looking for the antiderivative.
the antiderivative of cosine is,
Is sine.
oh, it's not negative sine?
Now, what's the derivative of sine?
Cosine.
Cosine. So sine's the antiderivative of cosine. So that's what we're messing up. Okay. And now, when we calculate the area, what do we get?
1 minus 0.
Yeah, just 1. Isn't that crazy?
plus or minus.
The area right here is exactly 1.
But it's not a school, it doesn't, okay.
Yeah, it's not, no, because 1 would be like right here. So it has the same area as this square. That portion somehow is exactly the same as that portion.
Oh, that makes sense.
Yeah. Yeah, make sure your things make sense. Just think about it. You'll catch most of your mistakes. Right?
Mm-hmm.
We thought about it, did that make sense? Then we did it, we were getting negative area when we knew it should be positive. We figured, oh, made a sign error. Okay, let's do the next one. We're looking for the integral of secant times tangent of x. What's the antiderivative of that? Whose derivative gives a secant times tangent?
And secants.
Secant.
Yeah, yep.
So this is the same thing as the secant of x evaluated from minus 5/4 to 0, which is equal to secant at 0 minus secant at minus 5/4, which is equal to secant of 0. Remember, secant is 1 over cosine. So let me just rewrite this down here one way in case it helps. Okay, that's essentially what we're solving.
So that's 1.
So what's cosine of 0?
1.
1 minus, what's cosine of minus 5/4?
Root 2 over 2.
Root 2 over 2. So 1 over root 2 over 2 is?
Root 2 over 2.
1 over root 2 over 2 is? The reciprocal of root 2 over 2 is?
Oh, 2 over 2.
Which simplifies to?
2 over root 2 simplifies?
Yes.
What does that simplify to?
That's why I'm asking you.
But it's a square root.
That would have 1 out. Get 1 out. I don't know.
Okay, let's think about it in terms of exponents. 2 as an exponent, that's 2 to the 1, times square root down here, that's 2 to the negative 1/2. So that helps you.
Root 2.
Which is what?
Root 2.
Root 2. Look, this is root 2 squared. Cancel out one of them. You're left with the root 2.
Oh, that makes sense.
That's good. So minus square root of 2. Right?
Okay.
Let me grab the book to make sure we're not making any obvious sign errors again. Find these examples. No, we're not to that yet. We're not to that yet. We're on those ones. Okay, 1 minus root 2. Yay. Alright. Next one.
Okay.
Let's do its antiderivative.
Is that a dx on the end?
Yes, sorry. Now, if you're getting stuck on this, remember that that's the same thing as 3/2 x to the 1/2. So what's the antiderivative of this?
It's 6 over 4, which is,
Add 1 to the exponent, then divide.
Which is 3/2.
So we have,
So it's
even if we're just
1.
going to take it one step at a
3
time, it's
over
going to be
2, yeah.
3/2 times x to the 3/2 divided by 3/2 or times 2/3.
Which is just x 3/2.
Yeah. Okay.
So there's the antiderivative of this, minus, if you don't like that, remember that's the same thing as 4 times x to the minus 2.
Well, negative 4, yeah.
Oh, we just put the minus there. So we're just doing the antiderivative of that. So what's the antiderivative of this?
Negative 4 over 3 to the power of that.
What are you doing?
Yeah, negative.
Oh, that makes sense to you too? Okay. Add 1 to the exponent.
Oh, that's right. Just.
Oh, negative what? So it's net. So it's
Negative 4.
negative 4
X.
x. Yeah, it's
Or
a negative.
so, negative
Or
4x.
4 over x. Negative makes that one positive. You follow that?
Yeah.
Yeah.
Okay. And we're evaluating this whole thing. We're evaluating it from 1 to 4. So this is equal to, plug it forward to this thing. Now remember, that cancels out with that, so we just have x to the 3 halves. So 4 to the 3 halves is?
2.
Perfect. Is it?
I have no idea how you did that.
It's not 2. 3 halves is more than 1. You're starting with 4. You better end up with a bigger number or you've done messed up.
Oh, it is backwards.
Isn't it squared and then rooted?
Squared and then cubed, square rooted and then cubed,
It's 6.
or cubed and then take the square root.
Yeah. So the cube of 4 times
No, take the square root first. Don't cube 4.
square root of 4 is 2.
Now cube it.
8.
Woo! Quick math. Plus, what do we get when we plug in 4?
Just what?
Worried you guys might miss that one. Minus, what do we get when we plug in 1 now?
Just 1.
1.
That's
4.
4. 5.
Can you do that whole thing?
4.
4.
Boom! Alright, there's the area. It's exactly 4.
Okay.
Nice of them to give us such a nice function.
It's nice.
That's why I like using examples from a book rather than thinking up stuff on the fly. Always comes out ready. Usually does.
Sometimes.
I have another calculus textbook and the author, oh, he expects so much of the students. He gives them hard problems.
Just pull stuff out the top of his head.
Okay, next one. Let's see. So, back to the example of chucking something up in the air. I take a marker, I throw it up in the air. It has an initial velocity straight up of 160 feet per second.
Okay.
Gravity is pulling it down at minus 32 feet per second squared. So the velocity function is 160 minus 32 times time.
Okay.
With me so far? Okay, so first our job is to find the displacement of the object over 8 seconds. And then we're supposed to find the distance that the object traveled over 8 seconds.
It's just an integral of velocity at 0 to 8, right?
Perfect. So we are just looking for the integral of our velocity function. 32t dt from 0 to 8. And this is going to give us displacement. When we go to get distance, we need absolute value. We need to make sure it's always positive.
That's right.
Make sense? So this is going to give us our displacement. It makes sense why this gives us displacement, right?
Yeah.
Velocity is the derivative of position, therefore position is what you get when you integrate velocities.
Yeah.
So if we have this velocity from 0 to 8 seconds, this will give us our displacement. Okay, this is equal to, what's our antiderivative? What's the antiderivative of 160?
160x.
160t in this case.
Oh, that's
Remember, we're doing time.
Yeah.
Yeah.
So we have 160t, for our parentheses there, minus what?
32 t squared over 2. Oh,
Perfect.
16. Jared had it.
So now, we evaluate this from 0 to 8.
Which is 0.
Well, you do the 8 first, this minus what you get when you plug in that.
Oh, that's right.
So when we plug in 8 to this thing, what do we get?
A really big number minus.
It's not that bad.
I don't know.
This is 2 to the 3 times 16 is 2 to the 4 times 10.
Okay.
So we're looking for 2 to the 7.
7 is 512, right?
No.
Or is it 2
You
to
can
6?
also just count. You know how to double in your head pretty easily if you can't do it.
Yeah.
One double is 2, 4, 8, 16, 32, 64, 128. See, not that hard.
Oh, I was waiting for that. Okay.
So 128 times 10 is
1,280.
1,280.
Subtract.
Now we're going to subtract away from it. 16, which is 2 to the 4, times 8 squared,
So
which is going to be 2 to the 6. 2 to the 3 times 2 to the 3 is 2 to the 6.
yeah.
So 2 to the
Which
10.
is equal to,
10,
So 2 to the 8 is 256, 512, 1024.
there you go.
Okay.
See? Not that bad. Now we take the difference and what do we get?
You get 256.
So there's our displacement, 256 feet.
It's a strong arm you got.
Isn't that 2 to the 8?
Yep. Wait.
It's just 128 plus 128, right?
128 plus 128 is 256, yep. Okay. I want to stare at it in the math to see if I can just see it, but we'll let it go.
Distance.
Okay, now we're looking for distance. I was just going to check the number if you got 256 as well, to make sure we didn't screw it. Now we're looking for distance, we need to do the absolute value of this thing, right? So now when I'm looking for distance, I need to do the integral from 0 to 8 of the absolute value of 160 minus 32t dt. Now I need to figure out what that equals.
Okay.
You with me?
If you,
How's
yeah.
that? Oh, I see. Yeah.
Because the absolute value of velocity gives me speed.
Yep.
So we're doing speed over 8 seconds. Adding up all the speeds over 8 seconds gives me my total distance. Good? Okay. Now, how are we going to deal with this darn absolute value? I know when I put a positive number into an absolute value function, it just spits out the number. I know when I put a negative value into an absolute value function, it spits out the negative of that number, right?
Mm-hmm.
So I need to figure out where this thing's positive and where this thing's negative. Where's my velocity positive, where's my velocity negative? The easiest way to do that is just figure out where is the velocity 0, and then it's going to be positive over some intervals, negative over other intervals. You've done this 100 times, right?
Yeah.
So where is the velocity equal to 0 in this?
When t is 5.
When t is 5, 160, yes. When t is 5, good. So when t is 5 is when it's 0. When t is less than 5, what do we get? Positive or
Positive.
negative? Positive over here,
And then negative.
and then negative over here.
Okay.
So this integral is going to be the same as the integral from 0 to 5 of just 160 minus 32t minus the integral from 5 to 8. Oops, I lost my dt. Sorry. dt minus my integral from 5 to 8 of 160 minus 32t dt. Right?
Yeah.
Okay, now we just calculate it as normal. So this is equal to, what's the antiderivative of this thing?
Just
160
160
minus
yeah.
60 squared.
So we're going to take this thing, we're going to evaluate it from 0 to 5, right?
Mm-hmm.
And then we're going to subtract this, the integral of this thing. What do we get for the integral of that thing?
Same thing.
Oops, minus 16 t squared, evaluated from 5 to 8.
Okay.
And that's going to be our answer. And obviously our distance is going to be way more than our displacement, right?
Yeah.
Because if I throw this thing way up in the air, and then I say after 8 seconds it's only a foot above my hand, the displacement's only 1 foot, but the distance was all the way up in the air and all the way back to that.
When you calculate, oh, never mind, you're right.
Okay, so this is equal to, we'll probably need a little bit of space. So this is equal to, when we plug in 5, what do we get? 160 times 5. What's 16 times 5?
80.
With the 0?
Yep, 800.
So we have 800 minus 25 times 16, or 5 times 4 times 5 times 4, or 20 times 20.
What?
However you want to think about it.
Isn't it just like 5 times 80?
It's just 80. Oh, no, it's not.
No, it's not.
No,
You can't do that.
16
It's
times
not
25.
40.
No.
No, it's not.
What's 20 times 20?
What's 2
400.
times? Look, that's 4 squared times 5 squared. Right?
Yeah.
Which is the same thing as 4 times 5 squared.
Okay.
20 times 20. Okay. Minus what we get when we plug in 0. Obviously we get 0.
Yeah.
So we don't need to worry about that. Now we have this minus sign. So minus what we get when we plug in 8 to that thing. We already figured out what we get when we plug in 8, right?
Mm-hmm.
What do we get when we plug in 8?
256.
That's when we get 8 minus what we get when we plug in 0.
Which is 0.
So 256. And then subtract, what do we get when we plug in 5?
400.
400. And remember, we knew that we had to take away whatever this number came out to, because we knew this number was going to be negative.
Yeah.
Sanity check, that better be negative. Is it?
Yep.
So we're on the right track. Okay, so this is equal to,
544.
did you just do it all in one go? So this was 400. 400. And then we're going to have, what's this one?
144.
144 that we add. So it's 544 feet was the distance covered. That's pretty cool. And better be a lot more than the displacement, which it is. Or at least more than the displacement. We could be talking about things just as we turn the corner. 544. Okay, we got it right. Okay, next. Compute the definite integrals of x squared minus 4 and 4 minus x squared for negative 2 to 2. So let's get a quick feel for both these functions we're talking about. So we're talking about two functions here. I'll call f of x equal to x squared minus 4, and I'll call g of x equal to 4 minus x squared. Okay, so we're going to integrate both of these from negative 2 to 2. But these are just inverses of each other. They're the same parabola flipped across the x-axis. So notice that this is just a negative of this. So if we graph these things, just to give us a feel for it, when we graph x squared minus 4, that's a parabola that comes down here to minus 4. So minus 4, parabola shooting up like that. This is f of x. You with me?
Yeah.
And then g of x is the same parabola, just pointing downwards. This is g of x. So when I calculate the integral from negative 2 to 2 of f of x, I'm going to get a negative area. And when I calculate it for g of x, I'm going to get the same exact number except for positive. Or at least I better, or we done messed up.
That's right.
So that was what part A is. They want us to calculate these things. So we want the integral from -2 to 2 of x squared minus 4 with respect to x. What's that equal to? Antiderivative of x squared is
2 is
X to the 3 over 3,
minus,
4x.
and we're going to evaluate this from -2 to 2, which is equal to, when we plug in 2, what do we get? We get 8/3 minus 8. Did I do that right? So 8/3 minus 8 is -16/3. Did I do that right?
sure we did.
I can't do that fast.
Well,
X minus 8 is.
That's right.
Yep.
that's right.
Mhm.
You just tell me, just keep moving. So that's what we get when we plug in 2. Now we got minus what we get when we plug in -2. Right?
Yeah.
So minus what we get when we plug in -2. When I plug -2 into this, what do I get?
-8.
I have minus 8/3 plus 8.
Oh, so it's just positive 16/3.
So positive 16/3, but we subtract it. And so all in all, it's -32/3,
Oh,
which is a negative number. Good.
that's right.
So now, let's do the same integral, or same bounds, but different function. This time we're doing
4 minus x.
4 minus x squared. This is equal to 4x minus x cubed over 3, evaluated -2 to 2 is equal to, what do you get when you plug in 2?
Is that a 3 or a 2 over there?
Sorry, I'm not sure. This one?
No. Yep.
Oh, yeah.
That's
Mike, yeah, that's a 3.
You
What's
get
wrong with it? When you plug 2 in there, what do you get?
16/3.
That was some quick math. And we're going to subtract what?
No, you're not going to
-16/3.
subtract, you're going to add.
You're going to minus -16/3.
No, yeah.
Behold.
Behold and love. And it's commutative.
It is 3.
Oh, and they cancel each other out to get 0, right?
If you do both of them, the point is they give you the exact same value, just one negative, one positive, which we'd expect.
Okay.
That was part A. Then we're supposed to find the area between the graph and the x-axis. Okay, the area for both of them is just 32 over 3,
Yeah.
right? Because there's really no such thing as negative area. How big is your house? -27 square feet?
Give or take.
Doesn't make sense.
Yeah.
Okay. We did that. We did that. Example 7.
What was the B even asking for?
The area. So first it says calculate the definite integrals, which is this and this. Now it says calculate the area between this curve and the x-axis, which would be 32 over 3. Then the area between this curve and the x-axis, which would be 32 over 3. So it's just now positive, so yeah, nothing new. I'll do one more example, then call it good. Figure 5.21 shows a function that, between that, the definite integral 0 to pi. Oh, we already showed a picture for a cosine function, so let's do just the last example. Find the area of the region between the x-axis and the graph. F of x is equal to, so we have f of x equal to x cubed minus x squared minus 2x. And we're doing on the interval -1 less than or equal to x less than or equal to 2. And we are supposed to find the area of the region between the x-axis and the graph. Okay, got that back going. Okay, so we're looking for the area between this and the x-axis, which means we need to know where it's positive and where it's negative to break up our bounds of integration. Right?
Yeah.
So we need to figure out where this function is positive, where it's negative. That's all we need to figure out, which is easiest if we just figure out where is it 0. So let's rewrite this factoring. If we factor out an x, we get x times x squared minus x minus 2, right?
Yeah.
Which is equal to x, let's factor that. What do we get?
Factor what?
Factor this.
The inside?
Didn't you already factor it? Holy heck.
We can factor that.
X.
Added together gives me that, multiplied together gives me that. In other words, it's going to
Minus
be...
1 plus 1.
No, that doesn't work. Try again.
Minus 2 plus 1.
There we go. Minus 2 plus 1. So where is it 0?
At 2 and at negative 1.
And?
A 0.
So whatever this function looks like, we know it has a 0, 0, a 0 at, sorry,
2.
2, and a 0 at negative 1. So there's the zeros. Obviously, we only care about from negative 1 to 2, so we don't care about over here, we don't care about up here, we just care about these two.
Okay.
So when I plug 1/2 into that function, do I get a positive or a negative?
Negative 1/2?
If I plug in, oh yes, thank you. If I plug negative 1/2 into the function, do I get positive or negative?
It's positive.
Negative 1/2.
You get positive.
Positive. We got a negative, and a positive. Multiplied together gives me a positive. You follow that?
Oh. I was looking at the. Okay, yeah.
Okay. Then I'll plug in a number like 1.
That's negative.
Negative.
Okay. So we can integrate from negative 1 to 0, the function, and then integrate from 0 to 2, the negative of the function, and that will give us the total area.
Okay.
Okay.
So we are looking for the integral from negative 1 to 0 of x cubed minus x squared minus 2x with respect to x. We're going to do that, and then we're going to do minus the integral. Let me put parentheses there. Minus the integral from 0 to 2 of the exact same thing, x cubed minus 2x, x cubed minus x squared minus 2x dx. Agreed?
Yeah.
Okay, so now we just got to calculate this thing. What's the antiderivative of this?
X over 4 to the power 4. I mean,
We have x to the 4 over 4 minus x to the 3 over 3
Minus x squared.
minus x squared. So we're going to take this whole thing and evaluate it from negative 1 to 0. And then we're going to subtract, parenthesis, the exact same thing. Except for this time, evaluated from 0 to 2. You with me? So this is equal to, for the first one, plug in 0, what do we get?
0.
0. Minus, what do we get when we plug in negative 1?
1 over 4 minus.
So here we got 1/4. Then we've got minus
Or plus.
plus a third. Then we've got minus 1, right?
Yeah.
Yep.
So let's see. I think we're going to do this in terms of 12ths. 3 plus 4 is 7. Minus 12 is negative 5. So minus negative 5/12. Did I do that right?
Yep.
Yep. So it's just 5 twelfths.
Notice it comes out positive, and we know that the area should be positive here. So that's good.
Yep.
Yeah.
And then we're going to do minus, and now this one better come out negative. When we plug in 2, what do we get?
64 minus.
Maybe we can do it here for a second.
3/3.
We get 4 minus
8/3.
8/3
Minus 4.
minus 4.
So it's
That's
just
just
negative
negative
8/3.
So it's just negative 8/3 minus what we get when we plug in 0, but we already know when we plug in 0, we get 0.
Yeah.
So, notice it came out negative like we expected. So now we have 5/12 is this. 5/12 plus 8/3. What's that going to be?
Which is 37 twelfths.
What? I have no clue you just said.
Because
So
you're
no.
multiplying it by 4. 37 twelfths. 4/16.
No, yeah, it's 32.
Oh my
That's
goodness.
five.
You are right.
Yeah, you're right.
I was thinking so weird. It's a good thing you guys are here. It's 37/12. And we'll check with the book. 37/12.
That's sweet.
So there it is. And that concludes the lecture. You can use all of the rest of class for homework.